Hello, this is Seminim, an assistant professor at Kunming University and also a first PhD at the University of California, Irvine. I'm so happy that I could finally introduce one of our works, Bancroft, Genomics Acceleration Beyond On-Device Memory. I'd like to share one of our research collaborators saying first. We have been learning a single next novel instance, which is the state-of-the-art and hot application for genome assembly for 1 year on a 1 terabyte AWS instance. We hope it will finish soon. This thing is very representative of the importance of acceleration in genome applications, which is essential for reaching 200-year-old life. So let's look at why these uncontrollable situations have occurred. These machines are very high-tech genome sequencing machines that have been released in the last 20 years, but they're still evolving at a very rapid speed. So thanks to the rapid advancement of genome sequencing technologies, the cost for sequencing have reduced exponentially, and the projected growth of genomic databases is expected to outpace even Moore's law. Due to the demise of Moore's law, technically due to the power and utilization work, but anyway, for such a scalability problem like genome analysis, leveraging hardware accelerators such as GPUs and FPGAs is a great choice, thanks to its massive parallelism and pipelining. So to the best of my knowledge, hardware accelerator platforms are usually equipped with tens of gigabytes, and the size of onboard memory is insufficient to support a real-world genome dataset. Some GPUs are equipped with up to 20 gigabytes each, but this number is also very small compared to the real-world scale. Then the data must be stored in host-side storage and moved over a slow PCIe or network connection. This incurs the most significant bottleneck in terms of performance using acceleration platforms like this figure. Probably the best solution to overcome the slow interconnect would be send as many data as possible within a limited budget of the bandwidth, right? So the common solution is data compression. Compressing data before PCIe transmission improves effective bandwidth. We have done this a lot for scientific data, text logs, time series, etc. But the problem is that compression doesn't work on genomes. Our compression algorithms get almost no compression, and the famous D-flat LG of course show almost no compression, but even genome-specific algorithms like DNA-bit are not enough at all due to the high entropy of genomic data. Then we might have a question here. Is there any good compression method for genome data? There is consensus-based genome compression. This algorithm tries to find quite long matches in a reference genome as shown in this figure, and stores match information like storing the offset of the consensus sequence as an index whenever possible. This is really good and can achieve very high compression up to 1000 or even more compression ratio. But unfortunately, consensus-based genome compression on a CPU requires just about 1 gigabyte per second effective bandwidth. It seems that this problem comes from variable length matches. If we do use variable length matches, many static trees should look up for every character in the compression phase, and we should do lots of shifting to compact matches into a continuous sequence in the decompression phase. So in other words, high compression ratio does not and actually cannot translate to high PCI bandwidth. Therefore, our solution involves hardware algorithm co-design, which is the most significant contribution of our work, Bancroft. The concept is quite straightforward. Variable length matches incur severe limitations in terms of throughput, so we delete them and make matches always follow fixed length k. Now the matches can be discovered with a single hash table lookup, a faster way than variable length matches. Additionally, we make mismatches always follow a fixed length stride, so now compaction requires only fixed width shift, not variable length shifting. Then will this restriction harm the compression ratio? Yes, variable lengths can find exact matching sequences by regulating the length, so of course this restriction literally restricts the high compression ratio. So we need a method for reclaiming compression. By default, fixed length matches K need to be quite large for compression to be useful. This is actually obviously right because matches must include an offset of at least 32 bits, considering the size of the reference data. But if K is 16, there's no compression. We can actually express genome sequences in 2-bit because the sequences consist only of characters A, C, G, and T. So 16 bases with 2-bit encoding is not a good idea because avoiding a 32-bit sequence encoding by a 32-bit offset encoding is meaningless behavior. Then what if 128K? For an ideal and desirable situation, if K is 128, we can achieve 8x compression if all k-mers matches, but usually this does not happen because the larger fixed K typically results in many fewer matches. So our solution for reclaiming the compression ratio is to use continuation and not encode the offset. For example, let's suppose if the previous 128 k-mer was matched, and we just found out that the current 128 k-mer is also matched, then we do not need to encode the current offset because we can use the offset of the previous match. So as you can see in this table, we can use continuation by just a 2-bit header, and we will show how our encoding scheme is effective on the later slide. But let me briefly say this method shows a quite compatible compression ratio than the state-of-the-art genome compression tool. So 16K has no compression, 128K results in lower matches, then the number for K between 16 and 128 would be good. For example, suppose we use 64K, then the bit length would be 128 bits. However, DDR4 and HBM's memory interface is usually 512 bits, so if we use 128 bits for each K, it would be a very poor decision. To solve this, hardware coalesces consecutive lookups if addresses are also consecutive. So to overcome the severe memory access latency that reaches 200 or more cycles for each lookup, which significantly degrades performance, we optimize fixed length matches through a group headered encoding scheme as depicted in this figure. As shown in the left side figure, 32-bit grouped header encoding comprises 16 2-bit headers similar to group bar int and enables the parser in the decompression accelerator to identify consecutive elements quickly. So in other words, using a grouped header, the decompression accelerator in Bancroft can support up to 16 lookups determined in parallel. So did our optimizations impact compression? To prove how our methodologies are impactful on the throughput and compression ratio, we did exhaustive problem space exploration, and to be honest, it was very painful. But anyway, so the answer to the question is that yes, of course, compared to a more thorough search. We did check the compression ratio by regulating the stride from 1 to 64, and also try to find the best k-mer size by varying the k-mer size from 32 to 512. After that, we eventually could get the most powerful parameter for the stride and k-mer. It was 16 for stride and 64 for the k-mer. So by using these numbers, we get over 10x compression efficiency and achieve a comparable compression ratio to other state-of-the-art genome compression tools that mostly focus on the compression ratio, not throughput. Not only achieving a reasonable compression ratio, our optimizations we did are to overcome the bandwidth bottleneck and achieve a very high effective bandwidth. Using Bancroft, users can experience 160 gigabyte per sec effective bandwidth by deploying multiple decompressor modules. I will introduce how we can finally achieve this effective bandwidth number in the later slide again. So, to build up Bancroft as a prototype, we used the Xilinx Argo U50 data center accelerator card, which is a mid-range ultra-scale plus card with high bandwidth memory, and we can deploy multiple parallel decompressors and compressors because as depicted in the left side table, the compressor and decompressor only consume about 4% and 3% of the chip respectively. The right side figure shows an example design with 3 decompressors and 1 compressor consuming 17 HBM pitches, which stands for shield channels. As represented in this figure, we can deploy multiple compressors and decompressors thanks to efficient hardware design that only consumes just a small amount of chip, like I said before. But we cannot deploy like 20 compressors or decompressors because of the size of the HBM. To store the offset of the reference genome as an index in the compressed format when the query is matched, we can use cuckoo hash off the table. But the problem is that we need at least 16 gigabyte for the cuckoo hash table, and this cannot be stored in RBO U50 with 8 gigabyte HBM. So we offloaded querying the offset table, performing the reference comparison, and encoding the compressed data to the host software. So as depicted in the right side figure, the hardware component is mainly responsible for computing the hash values for the cuckoo hash and performing probabilistic filtering using a smaller cuckoo hash to reduce the load on the software. That's why each compressor needs 2 gigabytes of HBM. Actually, using the probabilistic filter is one of our design's beauties, and I will show how this powerful component impacts the compression performance on the later slide. And each decompressor needs 768 megabytes of HBM, and this is quite straightforward because for the decompression task, we need to store a reference genome in HBM, and the 2-bit encoded human reference genome size is 768 megabytes. The size of the other species reference genome is similar as well. At the previous slide, I said probabilistic filter on the compressor, our Bancroft, is one of our design's beauties. The blue line here shows a pure software implementation, and the orange line depicts offloading hashing to hardware, and the gray line represents offloading both ASCII parser and hashing to hardware. We can see these are computation bound, since every new thread results in better performance. Also, we can notice that this implementation did not result in significant performance improvement, even though the only work left for the software at this point is cuckoo hash lookup. We discovered the 32-bit random access into cuckoo hash was causing excessive cache misses, turning the host memory system into the bottleneck. So Bancroft solved this problem using the probabilistic filter and reaches maximum performance with only 16 CPU threads. So Bancroft achieves 160 gigabytes per second effective bandwidth at the previous slide, and finally we are here. When my advisor and I look at this graph, we sometimes say our lifespan has probably been shortened by almost 2 years just for making this graph. Sorry about the joke at this big conference, but anyway, this graph shows the achievable effective bandwidth when users use our Bancroft with 10 decompressors with the acceleration platforms equipped with power throttled HBM. Bancroft with power throttled HBM overcomes the memory capacity and slow interconnect bandwidth issue and achieve DRAM level effective bandwidth, and that number is actually 34% of low HBM. But if we use non-power throttled HBM, that is usually equipped on Xilinx RBU U50C, U55C, and so on, Bancroft eventually achieve 160 KB per second effective bandwidth without PCI pressure by a hardware co-design compression algorithm and effective hardware accelerator designs with no IDEA. So this number is almost 2x DDR4 and 31% of low HBM, and Bancroft can thrash PCIe at DRAM level bandwidth by using only 30% of the chip space. And all Bancroft achieves superior performance compared to all system-based. We also wanted to emphasize that Bancroft's decompressor achieves this while consuming only 3% of the U50 chip, while GPU implementation uses all available GPU resources. Bancroft achieves almost 100x the performance of one of the FPGA implementations, ALM50, and this is a very impressive number, we think. The purpose of implementing Bancroft is to support the state-of-the-art and important genome applications that suffer from the explosion of genomic databases through its high throughput and very reasonable compression ratio. So we picked the real-world usage case, which is pre-alignment filtering the important genomic applications these days. We implemented a shifted Hamming distance filter on Bancroft for pre-alignment filtering, and compared it with the state-of-the-art GPU implementations, which shows very nice performance so far, and also compared it with very ideal case of FPGA implementation without Bancroft. While many state-of-the-art pre-alignment filtering accelerators achieve very high internal throughput, performance when integrated into an end-to-end system is primarily limited by PCIe performance, resulting in the 3% and 4% utilization numbers presented in this figure. So thanks to the efficient compression implementation, Bancroft can greatly mitigate this problem within last generation PCI Gen 3 performance limitations, improving the effective performance of the pre-alignment filtering accelerator within an end-to-end system by almost an order of magnitude. So as we all know, Moore's law isn't going to save us, so we need to bridge the silos. Thank you for focusing on our research, and I'm more than happy to answer your questions.